Hi, my name's Tom Warner, and I've created a video series on lightning. And it's my hope to kind of share with you what I've learned as I researched lightning over the last 20 plus years. And this series will cover a number of different areas. We'll look at storm electrification, essentially how storms electrify and start producing lightning. And we'll get into leader initiation and development, how the lightning actually begins and how it develops. We'll look at the differences in the leader development. There's actually a positive and a negative end. It's a bipolar, bidirectional process, and we'll look at the differences between both ends as they develop. Then we'll take a look at cloud flashes, which are the type of flashes that remain within the confines of the cloud, and in some cases will reach outside the actual cloud itself, but it doesn't touch the ground, so we classify those as cloud flashes. Then we'll look at ground flashes, in which one end of the bidirectional leader will touch the ground and cause what we call a return stroke. And then we'll look at horizontally extensive flashes, and these are from storms, mesoscale convective systems that have large horizontal development, large charge layers that extend over, up to 100 and some kilometers, and that these flashes themselves can travel horizontally for great distances. And one of the things about these types of flashes is that they can lead to another type of lightning, which is upward lightning. And this is lightning that initiates from tall objects on the ground and actually travels upward. And that is my primary focus in lightning research. And we'll talk in depth about that type of lightning. And we'll get into transient luminous events, which are also caused by horizontal extensive flashes. And then we'll look at thunder and again get into the damage that lightning can cause. And finally, we'll wrap up with lightning safety. I'm going to talk about the many different types of lightning flashes up here on the left. This is a positive cloud to ground lightning flash, and we'll get into the different polarities and what that means. But this is a positive CG, cloud to ground flash, in which there was extensive spider lightning associated with it. These are positive leaders. We'll look at other types of positive CGs, which is an example here on the right. Negative CGs, which is here in the middle. And then, as I mentioned before, upward lightning was my primary focus in my research. And this is an upward lightning flash here in Rapid City, which was caused by a nearby positive cloud to ground lightning flash, which you see the return stroke in the background. And we'll again also look at some cloud flashes and the implications of those types of flashes. As far as background, I got my BS degree at the University of California in Davis in atmospheric science, and I selected that degree kind of by default. I needed a technical degree to be a pilot in the Air Force, which is what I wanted to do since I could walk. And I ended up getting a meteorology degree as that technical degree, and I actually fell in love with that type of study. Meteorology was very interesting to me, and what better way to be a pilot than to understand the environment in which you'd be flying through. And so in the Air Force, I flew the B-1 bomber, which you see in the top picture here, and I flew that for a number of years, and along with that, I also flew the T-38 Talon, which was the aircraft here below. As co-pilots, we got to fly that to build up airmanship, and then the Air Force sent me to Texas to become a T-38 instructor pilot. So I flew this aircraft as a instructor pilot for those going into the Air Force. I flew that as a student pilot, and then I became an instructor where I was teaching students. And it's the second trainer that you fly in pilot training, and then you go to your fighter or bomber track from there. After I got out of the Air Force, I remained in Rapid City, South Dakota, because that's where I flew the B-1 at Ellsworth Air Force Base. And I got into general aviation and became an instructor pilot and was teaching other pilots how to fly. And the chief pilot, Charlie Summers, of the T-28 storm penetrating aircraft, approached me and said, "Hey, do you want to fly an aircraft through thunderstorms?" And I was very interested. I had developed a very strong passion for severe weather during pilot training in Oklahoma, where I did my training, and that was the first time I got to see severe thunderstorms. And I just fell in love with storms. And so I had this growing desire to study severe weather, and now I was being approached with a chance to fly a plane through thunderstorms. Well, this isn't like any other plane. This is the only plane like it in the world that actually could safely fly through hail-producing thunderstorms. It was armor-plated, bulletproof essentially, and it had been flying through thunderstorms for about 30 years when Charlie asked me to fly it. And it was a National Science Foundation facility that was managed by the South Dakota School of Mines and Technology here in Rapid City. So I got to fly this aircraft, this amazing aircraft from 2000 to 2003. And you can see some of its features here. This leading edge was all armor plating to withstand hail. This canopy is not like a normal T-28. This is a 1949 T-28 trainer that's been modified. This is metal reinforced with these spars, and that's 3/4 inch Lexan plexiglass, which is bulletproof. You see this tube sticking out of the top. That's a chemical sniffer. Basically, it pulls in air, and it's an oxide of nitrogen sensor in the back seat. So the back seat was taken out, and instrumentation was put in there. It's a single pilot. You're there alone, and you're talking to a ground controller on the ground who can see your position as you fly through thunderstorms and kind of gives you an escape heading. They can see about a third of the data that we're collecting, and they can tell the hail size and the severity of the storm and kind of guide us through that storm. The aircraft had a number of different sensors. It could measure cloud liquid water, thermodynamic parameters such as temperature, pressure, humidity. We tried to measure particles from a micrometer up to 6-inch hail, and that was done through an array of instrumentation that would see the particle pass through an array of diodes that were shooting across an open receiving set of diodes. And as that particle went through, it took a two-dimensional picture from the shadow cast as the particle went through to measure the shape and size and concentration and all the properties that it could as those particles pass through the sensors. So you can see that these have a number of different sensors. We have temperature probes, again the armor platings on the leading edge of the wing, the leading cowling, and the tail, because that's the areas that would be receiving the impacts of the hail. This was again a particle probe, another particle probe on this side, liquid water content, another particle probe. And then we had a wing camera on the right side that would record our voice comments as we're flying, as well as see out the right wing. It also had a number of electric field meters, which allowed us to sense the ambient electric field that the aircraft was flying through, as well as the change that takes place from lightning flashes and flying into different areas of charge. So it was quite an aircraft. It was rated up to 3-inch hail, or designed to withstand 3-inch hail. I personally have never been in hail that big. A 1/4 hail was typically kind of the limit of what we flew through. But you can see that hail is something that can do great damage to an aircraft. This is the end of the wing, which is not armor plated, and you can see over the 30-year history it took quite a beating. And sometimes that was actually just beat out to kind of reshape it in the off season. But you can see here, this is where the armor plating is, and you can see that it withstands that just fine. This actually was a nice hemispherical part of the sensor when it was designed, and it took its beating over the years. So part of flying this aircraft was getting struck by lightning, which we actually did typically once a year for each of the three of us that flew it during the campaigns. And an interesting thing about the aircraft lightning strikes is that in most of the cases, the aircraft is what causes the lightning strike. And it develops due to the fact that the aircraft is enhancing the electric field locally as it's flying through these charge regions, or around these charge regions. And a leader, bidirectional, bipolar leader, will develop at two extremities of the aircraft and develop with a positive end and a negative end. And so the flash actually initiates from the aircraft. And this was key in verifying the theory that lightning develops in that way. And it wasn't until studies on aircraft lightning strikes that they were able to verify that in fact that is the case. Lightning develops in a bidirectional as a bipolar leader, which we'll see in more detail with the high-speed cameras later on. So we did experience lightning strikes. This is a strike that I experienced while I was flying through a rather strong thunderstorm, severe supercell thunderstorm. It is quite an experience. I describe it for me as getting kind of slapped on the side of the head or the canopy right next to your head. And you'll see in this video, which is on the dash looking forward, what that experience is like. You can see it initiates and there's the plasma as it flows over the canopy. It's because it attached to the propeller. And there was some subsequent strokes following that initial attachment. Wow. So you can see it does get our attention. And when we get down, we inspect the aircraft. And usually we'll find two burn spots. And that's where the attachment took place, where it initiated from. And typically it would melt away a little bit of the metal on the surface. In this case, it's the rudder, vertical rudder on the back of the aircraft and the propeller on the front, a little burn mark there. So that's why we had the two attachment points, and we would typically just file those out and inspect the aircraft, and usually it was the aircraft was good to go. Here's a typical profile of the flights that we flew. In this particular case, I used this data from this day and this particular flash to complete my master's thesis and publish a paper resulting from that. This is a lightning mapping array display. This is data collected by a lightning mapping array which senses lightning in 3 dimensions using the emissions that the leader tips emit as it propagates through 3-dimensional space. Those emissions are received by a number of sensors on the ground that are located in different locations, and they triangulate the source location of those emissions to actually map the lightning using very small, 40 microseconds, even I think down to 8 microsecond windows as it propagates. And so what we're looking at here, if we're looking from the top down in this particular box here, it's the time coding is using a rainbow time coding over time. So the starts off in the blues, and you can see that time progress here at the top. This is time versus altitude. And so the flash starts, kind of climbs up, and then kind of continues or kind of restarts in the lower altitude. This is where the aircraft was relative to that, and it passes by the aircraft at 5 kilometers. And you can see that looking down upon it, here's the aircraft over a 30-second span, and this flash passed right by the aircraft, continued. You can see quite a distance as far as this is a scale of kilometers. So, well over 30 kilometers, closer to 40 kilometers in the east-west direction. And the radar depiction here is on the right, and this is the path that the aircraft took on this particular day. You can see we're downwind of the really heavy 60 plus dBz reflectivity at 5 kilometers altitude. And in this case, the video camera on the right wing that I talked about actually recorded some of that channel. And so I took that data that was collected by the electric field meters, which is represented here on the left by the XYZ components. So this is what the aircraft saw as a result of that flash. And then I modeled what the aircraft would see depending on different types of line charge, kind of simplified line charge representations, changing the polarity, the orientation, the charge density on the line, and tried to model and use that to try to characterize that channel as the aircraft saw it. And so that modeling and best fit, we were able to say it was negative and had a certain estimated charge density to do that simplification of a straight line lightning channel, and that was published in Geophysical Research Letters. So my lightning research, well, what got me started, the aircraft flew from 2000 to 2003, or I flew the aircraft from 2000 to 2003, and then they retired the aircraft, and then that following summer in 2004, I was filming a storm over Rapid City, and I experienced this spectacular upward lightning flash. And I had not witnessed upward lightning before this particular observation, and I was just amazed by it. It was just something to behold, and that got me very interested in the physics related to it, trying to understand. We had worked with New Mexico Tech and a lot of other universities and entities during our research projects, so we got to learn about the other fields, and specifically the instrumentation and such. So we had relationships with these colleagues, and so I reached out to some of them at New Mexico Tech and University of Arizona, Dr. Phil Kreider to be specific, and Dr. Paul Kreibel at the New Mexico Tech, and asked him about this flash, and they kind of explained that it was upward lightning, and that that's something that's been studied for a while, but I wanted to study it further. So that got me interested in looking to see what has been studied about upward lightning, what do we know, and just try to get smart about lightning. And that actually is what started my 20 plus career in lightning research, was this flash itself. So over the course of a few years, I started putting all kinds of cameras in my backyard and filming lightning. I have there's 10 towers in Rapid City that I can see from my backyard, and my gracious wife allowed me to put a bunch of cameras in the backyard and film lightning using these standard definition video cameras and digital still cameras. And after a few years of recording upward lightning using that, I thought to myself, it'd be really nice if we could slow this process down and see it at a slower rate. And I had been aware of Tim Samaris's work with high-speed cameras. I heard about him getting a hold of this camera used for filming nuclear detonations, and it sparked my interest as well. So in 2007 at the Storm Chasers Convention, I talked to him and I said, I know you're working with high-speed cameras and lightning. I'm interested in getting into that for upward lightning research. What can you tell me about it? And he was very gracious in sharing, what he uses, how he uses it, and it convinced me that high-speed cameras would be a great tool in studying lightning, and I was very interested in pursuing that direction. So in 2007, I got my first high-speed camera and started using that. At the same time, I started modifying vehicles in order to carry them. And I started out by getting this van you see here in the middle. I bought that in 2008, and then I started modifying it to house the camera and the optical assets. So this is what it ended up looking like. I had a platform where I could mount multiple cameras here. You can see looking out during actual observations, and obviously this has evolved into quite the creature. I have a number of different cameras where I worked with colleagues and used their cameras and incorporated my own cameras, and it became quite the observation platform for optical observations. So we have the high-speed cameras here, 2 of them. Here's a high-definition with a global shutter, digital still camera, and I think at one point I had 9 cameras operating out of this van at one time, and I was just by myself. I had a chair to sit in, my Captain Kirk chair, as I call it. You can tell, I'm a Star Trek fan. I'm able to operate the cameras, and I've had cameras sticking out of the roof, out of the back, out of the side. So I'd have standard speed cameras recording more of the all sky environment, and high-speed cameras trying to focus in more on the flashes itself. Along with that, I developed a truck that could not only film with high-speed cameras from inside the vehicle looking forward while on the move, but also it would record some electric field data with an electric field meter and essentially a slow antenna. And so I was able to get some electric field measurements as well in a mobile way. And so we would use these we would use these vehicles to position ourselves or chase storms, and then try to set it up to where we had 2 different locations, try to get some 3-dimensionality in our observations, and get the optical observations of lightning. But in order to research lightning, you need both optical and electromagnetic observations, because the optical assets are only good as far as you can see. You can't see inside the clouds. You can't see what's going on. You need radar data to look at what the storm is doing and how it's evolving. And so in 2008, shortly after I got the high-speed camera, that next year after I made my first year of observations, I attended a lightning conference in Tucson, Arizona, and met Dr. Marcelo Saba, and he had been working with high-speed cameras and who I consider to be kind of the pioneer of high-speed camera use in lightning research. I met him, and we developed a friendship and a collaboration that continues to this day. And he's really been my mentor as I've gone through this process. I also worked with Dr. Vlad Mazur, who was part of the research efforts in using radar to monitor aircraft lightning strikes, and was able to see the bipolar bidirectional leader development from aircraft as they initiate lightning flashes. And he also used high-speed camera of 1,000 images per second back in the late 1990s. And so this idea of using high-speed cameras had been around since late 1990s, early 2000s, and fortunately for me, the technology was really advancing when I decided to get into it. So I was kind of at the right time as far as when this was becoming a more viable research technique. And so we collaborated with other researchers, Dr. Marcelo Saba and his students and colleagues, as well as New Mexico Tech, who we worked with the T-28, using the lightning mapping array. So this is some of the instrumentation that is needed and that we used here in Rapid City during the upward lightning campaign that we conducted from 2012 to 2014. And these sensors right here sense the change in electric field. They're called fast antennas, and they just sense the electric field change, and you can have a time constant where it responds very quickly and returns back to 0 when there is a change, or have a slower time constant in which the perturbation due to the electric field change doesn't come back to 0 quite as quickly, and so you can see kind of the progression of the whole flash, and they call that a slow antenna. So we have fast and slow antennas for measuring the electric field change. We have an electric field meter that records the ambient electric field, just the value of the electric field at any given time. Here's another slow antenna that was from New Mexico Tech. These were from Brazil with Marcelo Saba's group. And we located these in different locations. So here's a remote location where we have electric field meter, and then a fast antenna right here. And then we also incorporated, like I said, the lightning mapping array, which is able to measure lightning in three-dimensionally in the propagation of lightning. So for 1 year in 2014, New Mexico Tech operated a lightning mapping array here during our what we call the Uplights campaign, where we're studying upward lightning here in Rapid City. So it takes a collaboration with other researchers, other equipment, to really observe lightning in the way it needs to be in order to better understand it, to analyze it, to see all its properties.
So now that you know a little bit about myself and my career and my background, we'll start off by looking at how storms electrify, how lightning initiates, how leaders develop, and those differences in the way a positive and negative leader develops, and their importance as it relates to flash types and the physics of lightning.